that's good. Hello, folks. Welcome back. So, one thing I want to say first off here, I realized there were 2 errors in homework 1 in terms of the information that was displayed in your results section. I believe I have caught both of them, but I wanted to make sure that I pointed them out to you. One was this number right here was pulling the count rather than the percent. And so thank you, I think that was Jing for pointing that out. The other one I caught when I was double checking the rest was this number right here, which was populated from something else. So if you have already submitted your assignment and you want to look back at it and see if you need to change anything, let me know and I can reset it so that you can go back in and edit your stuff, okay? And at any point in the semester, if you do turn in your work early and realize after the fact, oh wait, I got that one wrong, and you want to fix it before the due date, that's totally fine. The only catch is that I have to find a time to reset it when no one's in the database working on stuff. So that's the only trick. So please let me know if you do want to change any of your answers, those of you who have submitted it already. And always please let me know if I have screwed something up otherwise. I'm happy to change it. So that is ongoing. While I have this up, are there any questions on this?
Yes.
Yes, hit me.
So with that number, so where you were before, you said it wasn't correct?
So each of these zeros in here gets populated with your answers from above.
Oh, I was okay.
So there won't be zeros when you look at it. They'll switch to numbers. But what I had done mistakenly was pull the number from the number, and it was supposed to be the percentage.
That's okay. So I have blanks up at the top,
Yeah.
which is why I'm like, there is nothing that has a 0%. You know, okay.
Yeah. Yeah, so when I write these, I have to tie each of these numbers to an answer, and I tied it to the wrong one.
Oh, that's really fun.
So,
and
this one was tied to the wrong one too. So that, I just want to point out those two to go ahead and check.
And I was like, well, anyway, I could just look down there to find the answers from there. I didn't realize they were.
Yeah, nope, it's the other way around. Yeah, it's the idea is that I know that you have the right number. Can you tie the right words to the right number? That's what this is about. So yes. So other questions? Is anybody still having problems getting SAS to win or Stata to win? Please let me know if so. I'm happy to help. So you're good, Tanya? Still need help? Okay, you're working on a Mac? Okay. Can you send me the most recent version of your syntax where you're trying to say the let file save equal and the place? And because I've discovered that the Mac, after the client part, sometimes the slashes have to go the other way, and that was a problem. The client thing doesn't need to be there if you're using the H drive. It does need to be there otherwise, and we also ran into an idiosyncrasy where it was on the Mac, right? It wouldn't take the comma separated values file if it wasn't inside the H drive. I know, I'm like, I had no idea. So the next homeworks, I'm going to give you Excel files instead because those seem to work regardless, and there, so you won't have to save it as another file format. So I'm learning all these new fun tricks as well. But please let me help you if you haven't figured out how to get access to SAS or Stata yet to get it to cooperate.
You have office hours today?
Yes, office hours in this room or floating around depending on how people want to work. But yep. Okay. Any other questions? All right, well then I will shut this down and we can go back to our regular agenda for today. So last time we were talking about univariate hypothesis tests, right? Testing the sample mean against some population value, sample proportion against that, and then segueing now into univariate to bivariate. So that's where I want to pick up. So now we get to the point of testing actual interesting questions, answering actual questions here. Let's see, I'm on slide 20 of lecture 3. So moving to bivariate. Associations between different variables, 2 at a time for now. Associations among more than 2 variables at a time will be done in the context of a model. So that is our next unit. You get to start doing regression modeling. So it's going to be exciting, yeah. And what kind of measure of bivariate association you need depends on what kind of variables you're pairing. for each, we are going to get what's known as an estimate or a point estimate. Sometimes people put the word point in front of it. That just means like the one number that's supposed to summarize the relationship. And whether or not it is statistically significant. So this is terminology we're starting to introduce. Most of the time, what you're trying to answer is whether or not the association is different than 0, whether there is an association at all, 0 being the reference point. So I'm going to introduce this concept of testing associations against 0 with specific types of associations, but more generally, what we are doing is something called null hypothesis significance testing. Now, I'm going about this a different way. In your textbook and in other people's classes, they talk about this as sort of a general concept first and then give you examples. I'm going backwards because I have a hard time following abstract things without a working example. And so that's just the way that I think of things. It's like, let's introduce this general concept with specific examples, and then we'll return back to the general. So just keep that in mind. The one that I want to start with is Pearson's correlation. Pearson is a very important dude in statistics. May he rest in peace. So Pearson's correlation is for an association between two quantitative variables. So continue-ish would be the minimum requirement. The way that a Pearson's correlation is typically illustrated is in this type of plot down here. This is known as a scatter plot. Sometimes it's a scatter diagram, but the word scatter is always a part of the word. The idea is that on the x-axis, so on the bottom one here, you have one variable, and it's plotted against another variable on the y-axis. And each point is one coordinate. So somebody's value on x and somebody's value on y. So each person gets one dot. And the relationship between x and y is captured by Pearson's correlation as a linear relationship. So for instance, this picture here on the left is a perfect relationship. Pearson's correlation varies from -1 to 0 to 1, continuously within that range. So this is a correlation of 1. That means that people who are higher on x are higher on y also, always, uniformly. If you remember algebra, maybe, the slope of the line, that's what we're talking about here, the strength of the slope. That will come up in modeling next week, but I just want to foreshadow that. The next two pictures show a less than perfect correlation, but it's still positive, meaning that higher values on x tend to go with higher values on y, but not perfectly. The noisier it gets, the more scattered it looks like, the closer the correlation is to 0, which is the fourth picture there in the middle. If you're high on x, you have no idea if you're going to be high on y. There's no relationship between these two variables. No linear relationship, I should say, excuse me. And then we head over into the negative side here. And it's the same idea, only the pairing is backwards. So a perfect negative correlation means that if you are lower on x, you are higher on y. If you are lower on y, you are higher on x. And you can see that that can weaken as you get closer to 0. So the strength is conveyed in terms of absolute value. Like a correlation of -1 is just as strong as a correlation of 1. A correlation of -0.8 is just as strong as a correlation of 0.8. The sign gives you the direction of the association. The number gives you the magnitude. So 0 is no relationship. That's what we're typically interested in demonstrating is not true. So relative to 0, what is the association that we found? In terms of notation, the population version of a correlation is sometimes listed as this P-looking thing, which is rho. Yes, I loved your answers on your quiz. She's like, the one that looks like 0. Like, exactly, yeah, the 0-looking thing is sigma, the U-looking thing is mu, and this is the P-looking thing, which is rho. Most of the time you will see it reported as just R, which is the sample version. So in results sections, it's almost always R, if you're talking about a Pearson's correlation. There are lots of other kinds of correlations. Pearson's is one type. So when you're reporting this, you do need to specify that it is a Pearson correlation as opposed to some other flavor, because the other kinds of correlations also use R. Okay, how are we doing? Good? All right, good. How do we find it? Well, actually two more steps relative to what you already know how to do. Now I'm showing you the formulae. Let's go with that, yeah. That sounds fancy. I'm showing you the formulae, but again, I don't need to do this by hand and I don't need to memorize it. I just want you to get a conceptual understanding of how this works. So the first steps in trying to find a correlation between two variables, you already know how to do. Find the mean of each. So we have x bar and y bar, so two different variables. When we get to models, they'll have multiple x's and one y. And so I'm setting up that as an idea. So think of this as one x trying to predict a single y for right now. We also need to know what their variances are. So we have the variance of x and the variance of y. And variance is squared offness. So each observation minus the mean, that's the key idea, how far off you are from the mean. We square these, remember why?
So it doesn't equal zeros.
Yeah, it doesn't cancel, the positive and negatives don't cancel out. So the unsquared version of this is standard deviation, so the average offness. Note the change in notation. So before we just had like s squared for variance, I'm adding a subscript for variance of what to help us keep track. Okay, good so far? All right. Next up, something new, covariance. It sounds like just what you would think. Like, have you heard of co-sleeping? Cohabitation? What's the bad one? Codependent, right? This is covariance. It's the coming together of two variables in their original metric. So covariance is how far off the mean you are on x times how far off the mean you are on y. And because we want to keep track of whether the offnesses go together in the same direction or different directions, there's no squaring. So off from the mean of x times off from the mean of y, that's one value for each person, sum across people, and divide by n minus 1. So if we have a positive covariance, that means that higher x's than average tend to go with higher y's than average. Negative covariance means that lower x's on average tend to go with higher y's on average, and vice versa. So this is the basis of correlation, but we're not there yet. So here's that formula again. Let me give you an example. So let's say that I have a sample of 10 men, and I have each person's height in inches and weight in pounds. So if I calculate or estimate the mean for height in inches, let's say that's 72 and some change. Standard deviation, so on average, people are 6 inches off from the mean. That's the standard deviation squared is variance. Here's my range just to give you a sense of what this variable entails. Do the same thing for weight in pounds. If I use this formula up here, I can calculate covariance, and it comes up with a number of 135. That face, exactly. It's positive. So taller people tend to be heavier, but like how much is 135? I have no idea. And if I had measured height in feet and weight in kilograms, it'd be a different number. And I'd have no idea what that number meant either. So the problem with covariance from an interpretation standpoint is that it is metric specific. So this is 135 inch-pounds. What the hell is that? Correct. So we need to find some way of conveying the size of this relationship that neutralizes these metrics, that standardizes them. And that requires converting covariance into correlation. So that's the last step. Correlation is taking the covariance and standardizing it against the standard deviation of each variable. So now we're left with a number that varies from -1 to 1. And if I tell you that I have a correlation of 0.99, that's almost as good as it gets, right? You are almost guaranteed, if you are a tall dude, to be a heavy dude in this sample of 10 people. So a correlation of 0.99 has meaning in a way that 135 inch-pounds never will. So why am I even talking about covariance? Because in the rest of statistics, everything is about covariance. Variance and covariance matrices to describe multivariate associations between variables show up all the time. So take note, quant people, person who's trying to be quant cool.
So quant.
So yeah. So covariance plays a big role because most of the time you want to keep a hold of the metrics of variables to do other things. If you're simply trying to describe one relationship between pairs, correlation will do that for you much more readily than covariance. But covariance is a step to getting correlation. So another way of thinking about this is if we had z-scored x and y first and then computed their covariance, that would be the correlation. So, question?
Yeah, can you explain the SX and the XY under the code?
Yes. This is the standard deviation of x, this is the standard deviation of y, and you multiply them together. So yeah, it used to be just s before for standard deviation for a sample, but now I have to say which variable it's s for, and so that's why the x and the y show up here as this subscript. And so why is it s and not s squared? Because covariance is not squared. So they have to stay the same. Okay. So, what's not in the formula? Let me go back a minute here. All of these formulas have something to do with sample size, right? Correlation does not.
Correlation has nothing to do with sample size?
The formula doesn't.
The formula.
Once you know what the mean and the variance are, the formula for correlation is independent of sample size. So what can happen is that the correlation estimate can be biased in smaller samples. So you think about this. If I draw a line between 2 points, how well is that line going to fit?
It's going to be
Perfect, right?
Yeah.
So if I only have 2 people in a sample, and I calculate a correlation between their x's and y's, what's that correlation going to be? 1 or -1, right? If I add 3 people, no longer perfect, but odds are good, it's still pretty good, right? So it's easier to get a strong correlation in a smaller sample. So there is also a thing that you may see called adjusted correlation. It takes the correlation that you obtained and adjusts it for sample size, as shown. I will be honest with you, I have never actually reported this. I found it in a stats book and I was like, oh yeah, I remember hearing about that. But just in case reviewer 3 yells at you someday for reporting the original correlation, I want you to know this. So in software, it's an extra option that you can ask for to get the adjusted version. So the bigger the sample, the stronger the correlation, the less it's going to matter. Okay. So how do we know if this correlation is believable, is different than 0? Well, we turn to our friend T for that. So more generally, we're doing a null hypothesis significance test. That's the general term for this. It's the idea that what is the probability or the likelihood of obtaining the correlation that we got from our sample if in reality these variables are unassociated in the population? Is this significantly different than 0? So we're introducing a little bit of language to describe this. So a hypothesis is a statement about any kind of parameter. It's a belief. There are 2 specific types of beliefs that you will hear. Null hypothesis, you heard this term before? HO. It's a statement about the population being relative to some specific value. So the examples that we've seen so far, I showed you, remember the twinning example from last week? Wanting to know whether or not our sample of twins had a sample mean that was different than the expected population mean of 100. The null hypothesis in the expected is 100. A lot of times when you're testing bivariate association, your expected is 0 because you don't have any information in which to base it. There's no hard and fast rule, though, that it has to be 0. It can be any number that you think is truth, and you can test it against that. Like 9 times out of 10, though, the null hypothesis is no relationship. The alternative, then, is that there is a relationship. And this alternative can either be directional or non-directional. So this is where wording starts to matter. I have expressed the idea of non-directional as this not equal to, meaning I'm not camping in one direction or the other. I'm willing to accept that I could have a relationship that is different than 0 because it's positive or because it's negative. If you're only going with one direction, that's known as a one-tailed hypothesis test. And that's only appropriate when the other direction doesn't make any sense. So in this case, the alternative, oh, hang on, typo. Okay, let's see if you can spot it. What's my typo? AJ, see? Yeah, see, I meant to do that. Just making sure you guys are paying attention to the notation, I swear. Let me fix that. HA. Thank you. Nope, not Control A. Let's try that again. There. Shift A. There. Much better. Okay. And the longer your PowerPoint presentation, the longer it takes to save. All right. So how do we know if we should say that it's 0 or that we've got evidence that it's not 0? Here are the steps. More generally, we use some distribution to calculate a test statistic, some measure of the strength of the association that takes into account sample size, as well as how many things you are testing. So there are 4 letters up here, 1 of them Greek and 3 of them English, for reasons I have no idea. But you've met 3 of these before. The difference is whether or not you are adjusting for sample size in calculating your statistic. Almost always we're going to do that. So you've met T. If you are testing more than one association at the same time, T becomes F. We'll get there later. If you are pretending like you have an infinite sample size and you're not worried about that, that's where Z comes in. And Z squared is chi-squared. So what shows up on your software depends on which of these quadrants you're in. And thing, by the way, means when you're testing more than one association. So bivariate, there's only one association for right now. So we're in the first column here. So we'll be in the world of T. Then, how confident do you want to be? Yeah, absolutely.
99 or above.
Well, that's your choice. So it's if you want to be super duper confident that it's not 0, that's a harder bar to cross, right? The trade-off is that it's easier to say that it's not 0 if you're willing to be less confident. So you can specify this in terms of confidence around sort of how much of the region is expected versus unexpected, but most of the time this is phrased as alpha. Remember alpha? Aberrant or abhorrent, we're putting the two together. It's the outside. So how much of the time are you willing to be wrong? That's the idea. And often it's 5%. That's just a convention. Different fields have different conventions. It should also be informed by the severity of a wrong decision. So we'll talk about ways of being wrong here in a little bit. So there are 2 possibilities then in this sequence. If your test statistic, your T, your chi-square, your F, what have you, exceeds the critical value, so you put yourself out into the tails of the distribution, then you can say that you have rejected the null. It is really unlikely to find a relationship of this size if the true relationship were 0. It's so unlikely that I'm willing to say, nope, I reject. I reject the idea that there is no relationship. I have evidence to suggest there is one. So take that. The other thing you can say is, uh-oh, I'm wrong. I'm within expected in terms of the distribution. If I'm within expected, then I do not reject or retain the null. So this is something you will get yelled at if you get this wrong, okay? You can never ever say accept the null. I know it sounds like a semantic distinction, but it's one of those things that people will be like, I can't believe she said that. No, we do not reject or we retain. Because it turns out that the null hypothesis is really never true. You just need a big enough sample to say that.
Did you say fail to reject null hypothesis too, or is that?
Fail to reject. Yes. I did not reject or I failed to reject. I usually say I retained because that's not the same as accepted. But reject and do not reject are the classical ways of describing this. More simply, you would say that your association is significant if you reject the null, or it is not significant if you don't. Significant means aberrant, meaning it's way out relative to what we would expect. Non-significant means it's within the range of expected variation. Yeah, I already had an extra coffee this morning, so I'm doing lemonade instead. It's just, it's not the same. So for example, we had a correlation of 0.99 between height and weight. You think that's different than 0? Odds are good, right? You might want to temper that odds are good with how many people it's based on. So how we test a correlation for significance is with our friend t. We compute a t as follows. It's r times the square root of this term here, which is sample size minus 2, and 1 minus r square here. That gives us t. Do you want to see t again? Let me find t, our friend t. Is t in this one? No, t is not in this one. But we got this. Same idea. Wait, yes he is. There's t. Yeah, that's what t looks like. So we're computing a value where null hypothesis is smack in the middle, t is 0. The further we get to the right, the higher than 0 it is, that's a positive relationship. The further we get to the left, the lower than 0, then it's a negative relationship. So we got to figure out where on this curve our current relationship lands, and whether or not it's far enough over to say that it's outside of this expected region and into the unexpected. There we go. It was this one right here. So in this case, I have a t. I have to know what my denominator degrees of freedom are. It's n minus 2 in this case. I'm using a two-tailed test because I don't want to stack the deck in one direction versus the other. I'm willing to accept a positive r as significant or a negative r as significant, different than 0. Question?
Can you tell me how you got that df?
Denominator degrees of freedom is sample size minus 2 for
Always?
this. Yep.
Okay.
Yep. In addition to calculating, see the 2 is somewhat confusing because it's like you have to know two things. You have to know the variance and the covariance. And so it's like once you know one variance and one covariance, you can get the other variance back. So it's like two unique things. So it's the number of things you had to estimate relative to all the possible things you could estimate to try and describe a sample. So it's like the Weight Watchers points, right?
Oh yeah.
You've used another card, or Dealer, you've used another card, right? So now this is what's left.
So there's no situation in which my degrees of freedom would be like n minus 4 because I used 2.
That's next week.
Oh damn. Okay. I'll just wait.
Yeah. No, that's a good. It's exactly what's going to happen. Is because if I want to predict y right now, let's say I'm predicting weight and I have height. What else might predict weight?
Calories consumed.
Yeah, whether or not you're a football player, whether or not you're training for a marathon. I don't know. There's lots of things, right? Besides just that. So the more things I add in trying to predict something, I spend my points. Yep, that's exactly it. So the t critical value then depends on how confident you want to be. So if I'm willing to say only 5% of the time would I find a value as extreme as mine if it were really no relationship, then I have to have a t bigger than plus or minus 2.3. Positive 2.3 if it's a positive association, negative 2.3 if it's a negative association. If I want to be more confident, less likely to have made an error in deciding that something is significant, then I got to go further, t of 2.75. In this case, it doesn't matter. T is about 25. So that's whether you use the regular correlation or the one that's adjusted for sample size. T of 25. And then you get a p-value that's this. So have you seen this notation before? Okay, this is something I had to review what it means. So this is called scientific notation. When you get numbers that are super duper small, it's like, I'm not going to print like 8,000 zeros. I'm just going to tell you like what the first numbers are after all the zeros. So this is like, go 9 places out. 1, 2, 3, 4, 5, 6, 7, 8. When you get to the 9th, that's where your numbers start. So if you see something where there's an E with a minus sign, just know that that's a really tiny number. An E with a plus sign is a very big number. Right, math people? Okay. I have no idea. Anyone? No one knows what the E in scientific notation stands for? Would someone like to ask to Google for me?
Enormously large.
Enormous, yeah.
It says the letter E is used to be in the 10 to the power of.
See, that doesn't make sense because it's not like E is not base 10 like in everything else. Let's just go with enormous.
Okay, I like that.
Enormously small. So in this case, we reject HO. We reject the idea that there is no association. If there were no association, we would find a correlation as strong as 0.99, less than 0.0000000% of the time. Really unlikely. Now I made up 2 random variables with no correlation just to see what might happen by chance. 10 people. So we have the same denominator degrees of freedom of 8. If I pick 95% coverage, 5% outside the coverage, critical value is 2.3. In this case, I came up with a correlation of minus 0.13-ish, right? So these are the differences after correcting for sample size. So null hypothesis is 0. How likely is it that I would find a correlation of negative 0.1? Say it again. Negative 0.13. Very likely. Like, that's not very big, right? So it turns out that the t-value that goes with that is minus 0.34. Let me go find my picture again. So if 0 is right here in the middle, minus 0.34 is like, So yeah, totally within expected range. I do not reject or I retain. I say I don't have enough information to be able to say that it's not 0. Do you know when I would be able to reject if I had a correlation that small though? Let's look back at the formula again.
A huge sample.
There you go. Yep. Put like 1 million in here. You can end up with a correlation of 0.01 as significantly different than 0 if you've got enough people. That's why the null is never really true. So that's where the language comes from. So yeah, the more people, the bigger T is for the same R. Say that again. The more people you have, the easier it is to say the R that you found is different than 0. So R takes into account the size of the bivariate relationship in an absolute sense. T T balances that with the sample size. So working backwards, if I told you that I had a T of 25, that sounds like a lot, right? It could be a lot because I have 1 million people, or I have an almost perfect relationship. T doesn't tell you. It confounds the two. So we report R to describe the size of the relationship. We report T and the p-value to say how confident we are that it's we would not find a relationship that big if the true relationship were 0. Okay. Side note on reporting things. Any value that stops at 1 or -1, you don't have to use leading zeros when you write up a result section, but any value that does, you should. So for instance, I'm reporting T with leading zeros because T's can go above 1, whereas the R's can't. So R values, P values, anything that like 1 is the highest, you don't have to use leading zeros for. So, everything else you probably should. Okay. How are we doing?
Can you put them?
Sure. So if you're going to have leading zeros, let me say it this way. It's better to always use them than to never use them or to use them inconsistently. Because if you report T's sometimes without the zeros and sometimes with, then it gets confusing to read like how big the number is. So just being consistent is the key. Another thing too in write-ups, it personally bugs me, people who use dashes instead of real minus signs. It's like sloppy. So I figured out a keyboard shortcut in Word. It's Control M for minus, so that way I never do that. But I put one in your write-ups, so you can just steal mine if you want. So, do you want to see how to do this? Why not, right? Okay. It's real easy. So let's get the example 3 out. I'm on page 7. So I've got SAS and Stata, per usual. We haven't talked about all of the output yet, but we can do the parts that we do know. So this is example 3, page 7. In SAS, every piece of output that you would request starts with proc. Remember what proc means? Procedure, yeah. Yeah. Can you guess what core stands for?
Correlation.
Yeah. So on my proc core, because SAS lets you have more than one data set active in memory at a time, it wants to know which one you'd like a correlation from. So data equals as an option. So this is the same data set we've been playing with, the general social survey subset. I am adding an option here, COVE. Can you guess what that stands for?
Covariance.
Yeah, or feel free to read from the screen, always. I'm shameless in encouraging participation. Usually what I have to say is up here somewhere. Pearson's correlations, right? That's a default, but I include it just to make, because in another example later we're going to ask for other kinds, but this is what you get if you don't say anything. And ignore the rest of the sentence for now. Plots, it will make pictures for you. I'm going to show you something called a scatter plot matrix, which is pretty cool. And which variables would you like to include in this? And I am doing 3 versions of family income. The z-scored version, the one that's in thousands of dollars, the natural log transform version, and education. Because we're all here trying to get educated, right? So we can get some more family income. Is that how it works? No? It's a nice thought though, isn't it? So you're telling me there's not a linear relationship between education and income? Ah.
Maybe not a PhD.
Yeah. Yes. Well, I think about the people who make the most money. Like, who makes the most money in our society? Like CEOs and like Lady Gaga, right? And football players. So yeah, there's not a perfect relationship, but this is my analysis, right? This is my question today. So the first thing here, this table.
So she ran.
Yep. So in my so if you want to run it, you can. There's the example 3 SAS files and Stata files. But what I would have done inside the SAS window is highlighted it and hit run, and then this pops out. All right, so this thing then, the first row of this is covariance, and the second row is the variance of the variable in that row, and the third one is the variance of the variable in that column, and then degrees of freedom is the last. So if we start here, for instance, at number 44, that is the covariance between family income z-score and family income in 1,000. In thousands. Is 44 a lot? So think about this linear versus nonlinear transformations. You all nailed this in your quiz. Z-scores versus income in thousands. Is that a linear transformation or a nonlinear one?
It's linear.
It's linear. Z-score just shifts the mean to 0 and the standard deviation to 1 of the variable. So you wouldn't know it, but 44 is as high as it can go, given the scale of these variables. The covariance here has a special name. The covariance of a variable with itself is variance. Remember the formula? How far off on x, how far off on y? These are both the same thing. That's the same as variance. Degrees of freedom. Last thing. Most of these are 95, but one of them is 99. So they include this in the event of missing data. So n minus 2 means that 97 cases out of this data set had enough information to estimate the rest of this, but there are 2 more people who provided education than provided income. So the degrees of freedom are higher for that variable. Okay. Pearson's correlation then. Now we get into numbers that we know what to deal with. The correlation between family income in thousands and family income z-scored, perfect, because it's a linear transformation. That's the definition. Correlation between family income z-score and log transform, imperfect, but still very strong. Log transformations take the positive values that are extreme and reel them in to be closer. It takes the lower values and spreads them out. I can show you what that looks like as a picture. This is my scatter plot matrix. On the diagonal are histograms of each of these variables, and then we have a scatter plot on the off diagonal. So in this quadrant right here, row 1, column 3, you can see what happens to these super rich people in the original metric of the variable, in z-scores or in thousands, doesn't matter. The super rich people are way further apart than everybody else on the original variable, but less far apart on the x-axis, which is the log scale. So you get this sort of bendy looking thing here between the two. Pearson's correlation measures a linear relationship. So what it's trying to do then, if you can see my mouse, is try to fit essentially a line through this. Because there's a nonlinear relationship here, it's not being captured by Pearson's correlation. So this is something that we'll see in just a second more about. Pearson's correlation is a linear measure of association. If there are associations that are nonlinear, such as this one, it's not going to pick it up. But let's see if I was right. is education related to income? Where do I look? So, remember this is language, right? We're doing language in terms of words, in terms of symbols like row, and language in terms of telling SAS what to give us, and language in terms of learning what SAS gives us back. Because SAS is not friendly. No programs are. They want you to speak their language, not vice versa. So we have, organizing on this table here, Pearson correlation coefficients. So the first row of each of these is the R, is the obtained correlation value. So the correlation between, say, education as the row 4, it's correlated with family income, 0.45. So what do you think about that?
Medium likeliness.
Association. Yeah, so are more educated people more likely to make more money or less money? More. More-ish, right? Yeah. Yeah, question mark. Yeah, so it's not 0. 0 would mean no association. A negative number would mean that getting educated is related to less income. We don't want that. So it's positive. Now, is it different than 0? Next row. Prob greater than R in brackets. What's that mean?
Can't be negative.
Absolute value, yeah. So this is the idea that we care about the size of the R, and that an R, say, of 0.4 is just as important as an R of negative 0.4. So it's testing you, it's telling you I'm not worrying about the direction here, I'm just worrying about the size. Probability of the absolute value of R, probability under HO, null hypothesis, that row, population R is 0. How likely is it that we would find a correlation of 0.45 in our data set if, in reality, the correlation is 0? How often would that happen? Less than 0.01% of the time. So they're skipping the step of giving you the t-value that goes with this and just giving you the p-value directly that it's computed. The correlation between education and family log income, slightly higher in the 4th decimal place, but not that different. So I would say that that provides a test of robustness. It's the idea that the correlation between education and income, like here's the rich people out here, right? They're not the ones causing the correlation. It's basically the same, even if you do a nonlinear transformation that reels them in with everybody else. And just because they're super rich doesn't mean they're super educated. So here's your hedge fund manager, right? Or your football player. So this is a prelude to fitting models. The idea of fitting models is to determine whether or not variables are associated and whether or not variables are associated uniquely. This type of scatter plot, this type of correlation matrix is almost always reported in result sections with quantitative variables. Knowing how these things are related to each other is a prerequisite to understanding how they're related uniquely, which is what we get to do next. Let's see. Yeah. And here is an example of how to zoom in on one of those correlations and get the regression line. So this is education versus log family income. That's this panel right here. Okay. How are we doing? As good as you're going to be? Okay. So, slight complication. Last time we found, in univariate hypothesis testing, right, we had a sample mean, we had a standard error of the mean. We used that to form some sort of confidence interval, right, to describe what the range of values in which the population mean is likely to fall. Well, we have the same idea here. We have this R. We can test whether or not it's different than 0, but we don't have a sense of how precise the R is otherwise. Like not 0 is not a good judgment. So we need the same kind of idea. Rather than a standard error of the mean, we need a standard error of the correlation. Right? We want to come up with a window that describes what, so R, the estimate itself, which is known as the point estimate, is the middle of the window. We want to be able to convey sort of how squishy it is. Like, is it like R or is it like R? Right? Because with fewer people, it's more likely to be R than R. But what's the highest that R can be?
1.
Or negative 1, right? And the R, for instance, in our example is 0.99. So if I had, say, a standard error of 0.03, and I took that and went 2 standard errors out, 0.99 plus 2 times 0.03 gives me above the boundary. So we have to find some way of building a window where the window understands that it can't go past the extremes of R. Like the mean can be anything. Variance has a boundary on one side, on the negative side. It can't be negative. Correlations are bounded on both sides. So in order to figure out what a confidence interval would be, we rely on our new friend, nonlinear transformation. Slide 29. This is another important dude in statistics, Fisher. He came up with a solution that allows us to transform correlations into a metric that is continuous. We compute standard errors and confidence interval limits in that metric and then back transform to R. His metric, by the way, he called it Z. And so this is known as a Fisher's R to Z. It's not the same Z as Z-score, though. I know, right? Take it up with him, right? He's dead, but I'm sure his descendants can fight about it. But it is like a Z in the sense that Z starts at 0, or the midpoint is 0, and it goes continuous in either direction. So this is a plot of what the Z to R transform looks like, where R is on the x-axis along the bottom. The transformed version of R that you get from that formula right there is on the y-axis. So this is a nonlinear transformation because it's using log-based E here. So it's taking the value of R that shuts off at -1 or 1 and stretching it out into positive and negative infinity. So you can ask for this transformation in order to get a standard error and a confidence interval, and then back transform that into R. That's what this extra code that I skipped over is doing. So Fisher, and then options within that bias adjust equals yes, mean use the version of the R that's been corrected for sample size. You can choose to turn that on or off. And I also gave you an example of how to test a correlation against another type of null hypothesis. Let's say that I had some reason to expect that the correlation between income and education is actually 0.5. And I want to do a comparison relative to that instead of 0. I can do that. I'm asking for it with an alpha level of 0.05. What would I change if I wanted to compare it to a correlation of 0.2? Yeah. Da. I'll show that again. Da. That's it. So that's this extra piece of output down here. It is giving every pair of correlations. So this is the one that we looked at in the plots most closely. So the sample correlation between log income and education was 0.45. So people with more money tend to have more education, or people with more education tend to have more money. We can't say which it is. It's just an association. If I translate that R into a Z, it's that number. So there's not much of a transformation needed because this is a mid-range R. Contrast that with, say, this correlation of 0.8 translates into a Fisher Z of 1.1. So it's stretching it out so that it doesn't stay with, it stretches the metric of the correlation out so it's unbounded rather than being trapped between -1 and 1. The bias adjustment column gives you the difference between the correlation that you computed just without paying attention to sample size and the one that is computed paying attention to sample size. So that's that one. Here's my confidence interval around that correlation. So 95% of the time, if I redid this study over and over and over again, the population correlation is supposed to be between 0.27 and 0.6. The last column then tests against my revised null hypothesis that the correlation should be 0.5. And I have a p-value of 0.53 against that. What does that tell me? Danae, have you lost your will to live? No? Just tired? Yeah. I'm tired too. No worries. So, okay, we'll walk you through this. Is this p-value less than 0.05? No. So 0.05 is the magic number here because that is where aberrant starts.
I'm sorry I talk so much, and I talk out loud too. So 0.05 is the one that's on the outside, like in the tips of the outside.
Yep.
That's what you want, meaning we can believe that this is significant because it would be so hard to get to the tips.
Exactly.
Okay.
Way unlikely. Yes.
I'm thankful that you asked a lot, because sometimes I have the same question and I'm afraid to raise my hand.
No, talking is good. Talking is how you learn these things. So it's great. I wish everyone should talk.
I can bring it down a little bit.
But yeah, you want to be out in the tips. So in this case, I have an obtained correlation of 0.45. I am asking, is that different than 0.5? And the answer is no. So if 0.5 is the middle, and my obtained correlation of 0.5 is here, like it's not in the tail, it's well within expected. Another way of saying that is that the population correlation of 0.5 here is well within this interval. So I don't have enough evidence to say that 0.45 would be unexpected if the truth were 0.5. I do have enough evidence to say that 0.45 would be unexpected if the truth were 0. Most of the time, people are reporting associations against 0 as a null hypothesis. Exceptions would be if you're doing something like a meta-analysis or a lit review or something where like the same type of association's been found over and over again and you want to see if your sample matches what's been in the literature, then you can specify another one, and that might be of interest in those cases. Okay. Words. So how would I describe this? We estimated Pearson's correlations. So right there, I'm saying that italics R is now going to mean Pearson's correlations everywhere else in this paragraph, so I don't have to type so much. To examine the extent of linear relationship for years of education, so I'm giving descriptives for that variable, with 2 variants of family income, logging thousands of dollars or natural log transformed income, 2-tailed alpha of 0.05. So that tells me 2 things. That I am willing to accept a correlation being greater than 0 or less than 0 is meaningful. That's the two-tailed, two sets of extremes instead of just one. And that I'm defining aberrant as 5% of the time or less. That we would find it that infrequently. And we used, I always write in, try to write in not passive voice, that bugs me. So we used, right? Even if it's just me, we used. Fisher R to Z transformation to compute 95% confidence limits around the correlation estimates after adjusting for sample size, defining another acronym here. So R is the population correlation, R adjusted for sample size, I'm putting a subscript of adjusted on here. Given our sample size of 96, degrees of freedom is 94. Years of education was significantly positively related to family income in thousands. Stats. Remember the two parts of every results section? The first part is in stat ease and the second part is in English. So, I've offset this with parentheses in this case because I don't have any interior parentheses and there was a lot to put, so I thought that looked better. So I'm using 3 significant digits for everything I'm reporting. My sample R is 0.452. That is P of less than 0.001 against 0. The adjusted R is that. And the 95% confidence interval for that adjusted R is that. Comma, indicating that greater education was associated with greater family income. And then the last part of that parenthetical is really for your benefit. I probably wouldn't put that in an actual publication. And then similar results were found using log transform income instead. So, and I think the air conditioning is kicked on. Whew. For Stata, it looks remarkably similar. Those of you who have to pledge allegiance to Stata, okay, listen up. Okay, I found out something very important. That core and PW core do something different with missing data. Core uses listwise deletion, meaning that if you ask for a correlation amongst 4 variables, it only does it for the cases that have all 4. Whereas PW core, which stands for pairwise core, uses all possible information, including partially missing observations. So you will not get the same results back from these two things. So I have that all written here, but just to do that. Stata apparently did not have a Fisher R to Z transformation thing included that I could find. So I asked the Google how to find it and found that someone had made one. So this is a couple times this has happened. So when people write their own little programs to do stuff for you, you can download them if it's like an officially Stata recognized thing. So I installed it and then used it. I am guessing that within your virtual desktop, it may not let you do this because you probably need to have administrator privileges. So I promise never to put anything in a homework that you need to download something extra to get to, because that doesn't seem fair. All right. Okay. Linearity. One last little bit here before we adjourn. So this is the scatter plot that goes with the 10-person data set that I used for these calculations. The correlation between height and weight is 0.99. That's the plot on the left. I made up 2 random variables that were not supposed to be correlated in the same data set, and here's my correlation of 0.08 in this case. So the steeper the line, the stronger the relationship. But it's always going to be a line. Pearson's correlation is not equipped to indicate nonlinear relationships between variables. So for example, this picture right here, best fit line would look about like this. That's missing the story though. So what this shows actually is a mixture population in which there is a negative relationship up to some point, followed by a positive relationship after that point. So this is not as uncommon as you might think. Like stress and performance, right? There's a classic U-shaped relationship. If you don't give a shit or you're too nervous, that's bad. But right in the middle is the sweet spot. So if you can think of this as like, performance as measured like where lower scores are better, you might see something like that. And so it would be incorrect to say there's not a relationship between these variables at all. It's just not a linear one. The only way that I know of to indicate nonlinear relationships like would be implied by this picture is through a model. So we're doing that next. This one is a classic case. I stole this from Wikipedia. This is somebody who is demonstrating that just knowing the correlation doesn't really tell you about the data itself. All 4 of these scatter plots depict a correlation of 0.82. So the first one, that seems pretty reasonable. Here we're clearly missing on a nonlinear relationship. Bottom left, this person up here is dragging the line. And here this person is really dragging the line. So pictures can still be helpful even with statistics. And a lot of times people may want to see them. But it's worth inspecting before you go too far. All right. So, wrapping up, Pearson correlation. What's it for? Relationship between what kind of variables? Quantitative, bivariate, yes. Linear, yeah. There's another correlation in town that's used for variables that are ordinal or quantitative variables in which you want to reduce the impact of extreme values. This is another important dude in statistics, Spearman. So Spearman correlation. Picture on the left here shows a data set in which the correlation either calculated with Pearson or Spearman would be about the same. The other pictures, they vary. How Spearman's works is you transform your data first. You sort your data in order, each variable separately, and you assign a rank. So the highest score is 1, second highest is 2, third highest is 3. You correlate the ranks. So it loses all of the information about how far away the values are. It retains the order. So if you have a variable like how happy are you on a scale of 1 to 5? Well, if I say like not at all happy, a little happy, somewhat happy, frequently happy, right? Those aren't really numbers, right? That's a categorical variable where the numbers are really just labels. But if you want to be able to associate that with another quantitative variable, this is the type of relationship that you'd want to see instead. Something to where it's really just based on the rank orders rather than the numbers themselves. So for instance here, this plot in the middle would be a Pearson correlation of 0.88, but it would be a Spearman correlation of 1. Likewise, this one is a Pearson correlation of 0.6, but it would be higher if it's 0.8. Spearman's would be higher because it's not penalizing from being this far apart. Like these would just be next in the rank, which puts it closer together. So if ever you are in doubt as to whether or not your quantitative variables would be eligible for a Pearson's correlation, ask for this one too. It may be an easier sell specifically if they're ordinal, or otherwise if you're worried about extreme values biasing the relationship, such as like in this picture here.
Is Spearman's row a different row than we were talking about before?
Nope, same row.
So he just grabbed it for every case?
Yep.
Gotcha.
Yep, it's rank order coefficient or Spearman's row, even though he means it for sample and not necessarily population. Yep, welcome to the inconsistency of notation. But yeah, I would just say Spearman's correlation, and then you can either still use R or you can use row. But it's sometimes called Spearman's row as well. So rank order is the key idea. So in SAS, to get that, I added the word Spearman. And then it spits out Spearman correlations and Pearson correlations. So we can look at that next time. Let me see. Yes. So foreshadowing that, take a look at these descriptive statistics here. I'm picking up some new variables. How often do you socialize with friends on a 1 to 7 scale? This is an ordinal variable. And how happy are you on a 1 to 7 scale? Another ordinal variable. So look at the mins and maxes. Socializing goes the full range of the variable 1 to 7. Mean of 4.3, median of 4. Based on those numbers, what shape do you think that variable has? It goes from 1 to 7. Middle is 4. Yeah, relatively symmetric, I would say. In contrast, happy, supposed to go from 1 to 7, only goes from 3 to 7, and it has a mean of 5.5 with a median of 6. Skewed, right? Everybody's piled up. Everybody's super happy, and then there's some people that are grumpy, like tailing off towards 3, right? Yeah, so these numbers can give you a sense of what the variable looks like even if you don't have a picture. But even though we're thinking of these as numbers, they're not really, because they're arbitrary, they're ordinal. I could have used like 1, 2, 27, 39, and 50 for what those labels meant, and that would be just as cool. So this is a case where Spearman's would be more appropriate. So that's what we asked for. I have the Pearsons and I have the Spearmans, and you can see the differences are slight in this case, but Spearman would be the one that would be more appropriate. Ta-da! Spearman works just like Pearson though. Ranges from -1 to 1, where absolute value is size, direction implies which way the pairing goes, and it's tested the same way with T and P and all that jazz. So for instance, this number right here, a correlation between how often you socialize with friends and the log of family income. So it's negative. So do rich people spend more time with their friends or less?
Less.
Less.
Which is surprising.
Significantly less?
No.
Here's my magic bullet.
Oh, yes.
Yeah.
So 0.05 is magic,
Mm-hmm.
and that's way out in the tips.
Yep. This is if there were no association at all, if the association were 0, less than 2% of the time would I find a correlation that strong. Well, if we accepted an alpha of 0.05 to start with, if we decide that's where, that is where expected and aberrant collide, at 0.05, then this is less than 0.05. So we would call that significant, reject the null hypothesis that there is no relationship. Because it's really unlikely we would find this if there were no correlation. Yep. Yep. All right. Words. So it looks the same, except I'm defining Spearman's rank order correlations as row. Also giving degrees of freedom in parentheses because they vary based on completeness of the data. N-2 is how we get that. So, questions? All right, we're done, right? Yeah. So let me know if you have questions about homework 1 or if you want me to reset it so that you can check your answers and change them if you need to, given what I said earlier. Otherwise, have a great weekend. Office hours later today if you need help. Yeah.
Or like we all submitted just so I can make that based.
Yep, I can do that.
Because I took a picture of it and I can see now where the error goes, but like on here, it looks fine. I just want to make sure.
That's fine. That's fine.
Standard deviation, whatever it is. Like, I use that for
I brought my lunch with me, so
with these semicolons.
no, I brought it with me. So I literally texted my school.
You can,
I know that.
if you wanna go to those.
I don't know if it's sick off. I get like
Last week I was sitting on my phone and she wanted to, and then I was eating my wheat. And I was like, it's so hard not to chew out. So I was like, one chew every 5 seconds.
That's funny.
That's what I think is
And I should just do that for certain.
Should they put like? It's like, it's based on a chart, right? It's today's, right? Yes. I did apologize. Oh my God. So like, so this is like, right, so that's why things are all the same. Because they're canceling each other out, because it's correlations of right, and so, no, I mean, out, but then she also did it.